Hello, welcome to this week 7 class on traffic engineering. So today we'll be discussing the planning and operational analysis of signalized intersection. So it's 2 minutes to 7, so I'll wait till say 7:05 and see if anyone joins, and then we'll get started with today's content. It's 7 p.m. already, but since only you have joined, so I'll wait for 5 more minutes and then we'll get started. So I'll wait till 7:05 to see if more people join in, and then we'll get started with today's session. Okay, so it's 7:05 already, so I'll get started with today's session. Welcome to this week 7 session on traffic engineering. So today's topic of discussion is, I think, planning and operational analysis of signalized intersections. So I'll get started with the discussion. I'll turn off my video and start sharing my screen. So the idea would be to first start with some of the concepts or numericals that have been discussed in the class. And then I'll go into the assignment problems that are there, similar questions I'll be solving in this session. So I think there was also one doubt related to some answer of the previous assignment, and I think in assignment 6 most probably. So I think few people posted it in the discussion forum. So I think the instructor should resolve it if it hadn't been resolved so far. So yeah, that's fine, I think. Okay, so I'll get started with the discussion. So let me share my screen. Okay, so hope it's visible. So let's get started with today's discussion. So the topic that will be covered today is first is pre-timed signal design. Now, in this context, there are different things that will be discussed. One is obviously the Webster's method. Then there are two concepts. One is critical lane and time budget concepts. And then you have this planning level analysis that was, I think, discussed in detail in this week. And then the main topic of discussion was, I think, this operational analysis of signalized intersections. So these are the main two things that will be discussed. There was another topic with, I think, on pedestrian signal requirements. It was, I think, discussed very briefly. So we'll be discussing it if we have time towards the end. So first, I'll be starting with Webster's method and maybe just give a brief overview, and then I'll move on to solving one problem if there is one in the assignment. So let's start with that. So Webster's method. So here, the main concepts or the main terminologies that you have to remember here is one is the cycle length. So there is a formula for this. So this is denoted by C0. So yeah, I'll write it like this here. And then you have different terminologies, right? Next is the loss time per cycle or per phase. You can think of it as this Li. Next is total loss time. This is denoted as L. Then you have number of phases, the flow on lane groups having the right of way during one phase, saturation flow of different lane groups, and this thing. So this also called as optimum cycle length. So there are different formulas for like calculating everything. Like for optimal cycle length, C0 in seconds, you need information on this total loss time per cycle, which is L. So you can write it as per cycle. And then you need information on maximum value of the ratios of approach flows to saturation flows for all lane groups using phase I. So this YI term is important here. So maybe I'll just quickly write it. So this Yi equals Qij divided by Sj. So we'll see one problem related to this. And lost time per phase, which is this small li, this depends on actual green time, the yellow time, and the effective green time. So the formula for this is actually this actual green time plus yellow time minus effective green time. This is for phase I, and total lost time will be sum of all these li's. It would be L1 plus L2 up to whatever phases you have, say Ln, and then you have all red. This is the total all red time during the cycle. Then you can also calculate total effective green time per cycle. So let's write it, total effective green time per cycle, which is simple G total equals C minus L. C is the cycle length. Then you can distribute it for each phase as well, depending on the yi values that I have talked about. And the actual green time can also be calculated through this formula, where you just take this gi and yi to the opposite side and you will get it. So all these are related like this. And I think there was one problem related to this in the assignment. So let me quickly open it and solve that problem. For that, okay, so let's solve that problem. So that assignment problem has, okay, let me include a figure and then I'll talk about it. So this is the problem data that you have. All the flows are given, southbound, eastbound, westbound, and northbound, and the phases and everything that you can determine. So phase A is basically eastbound and westbound. So this one. And phase B is northbound and southbound. And the saturation flows are also given. So you have to design signal using Webster's method. So let me write it down. Design signal timings using Webster's method. And you would need additional information. So this is given two-phase signal system, this intersection have. And the total hourly volumes for all approaches are like shown in the figure. And all red time is given. So let me write all red time per phase is 1 second. Then you have lost time per phase. This is equal, say, 4 seconds. Okay, so this is the data that I have. In addition, I will need the saturation flows as well. So let's write the saturation flows. So for phase 1, or sorry, phase A, this is eastbound and westbound. This is equals, so also, in fact, it would be different for this. So for eastbound, let's say this is 1200 vehicles per hour per lane. Then you have westbound, which is 1300 vehicles per hour per lane. For phase B, you have this northbound, which is 1400 vehicles per hour per lane, and for southbound, you have again 1400 vehicles per hour per lane. So this is the entire like problem data. So let's push it this way. Okay. So this is given to you. Now there are a bunch of questions that you have to answer using this data that have been given to you. The first one is the yi values that I have talked about in the previous slide. So it's the summation of all the yi values. So that's the first question. What is the value of, say, y1 plus y2? The number of phases that you have. Suppose I'm denoting it as n instead of I. So that is the summation of the ratios of approach flows to saturation flows for all critical lane groups. Okay, so you're asked this. Now, how would you approach this problem? So first is the phases are given to you. The lane groups are also defined. So EB and WB are like two lane groups here, and NB and South B, SB is the other lane groups that are there. The hourly volume or equivalent hourly volume per lane is also given. Like this is 340, 420, just 450 and 550. Saturation flows are also given. These are the values. It's now very simple to calculate yi values, so which is nothing but related to qij divided by that j, that ratio. So here I have talked about this briefly, I think. So this is qij divided by sj. And then you have to take, it's not actually the exact qij divided by sj, but you have to pick the maximum of all the lane groups that you have for that phase. So what you can do, you can create a table here and then you can solve this. So let's insert a table, cell painting. Okay, did someone get the answer? Let me check. 0.795 is the answer that you were saying. Okay, let's see if that's correct or not. Someone said 0.716, someone said, okay, 0.795. Let's see who's correct. So here it's the phase, then it's the lane group, then you have equivalent some hourly volumes per lane. Next you have saturation flow. Then you have this ratio Q Ij divided by Sj. Then you have to write this yi values. So now this is phase A, this is EB, B. For phase B, you have northbound and southbound. This is given as 340. This is given as 420. This is given as 550, and this one is 450. Saturation flows are also given. Eastbound is 1200. This is 1300. This is 1400. This is also 1400. Let's see what these ratios are. So get a calculator. So it's 340 divided by 1200. Okay, so it's coming out to be 0.283. Then it's 420 divided by 1300. So it's 0.323. Then you have 550 divided by 1400. So that's 0.390. Sorry, 0.393. And then you have 450 divided by 1400, which is 0.321. So here you have to pick this one 0.323, and here you have to pick 0.393. So if you add those two up, so the summation becomes 0.716. So that would be your answer. So let's the answer is 0.323 plus 0.393, which is equal to 0.716. Okay, so I think one of you got it correct. Yeah, 0.716 is the answer. That's correct. It's not 0.795. So yeah. And I'm not sure if the numbers are the same in this. Is it? Okay. It's slightly different. So I changed this saturation flow values, and this this all red and the other portions. So that's why maybe because of this your answer is coming. You perhaps mention the answer what is given in the assignment, but I'm not exactly solving the problem data that are given in the assignment. So yeah, we have to be careful what I'm giving here. So next, let's solve another related problem with this. For this problem, I'm not exactly solving the assignment. I'm not even sure what will be the answer for the assignment problem. So you have to work it out and check. Yeah. Okay, so let me move to the next problem. So the next one is the data remains the same. So it's as the previous slide, not in the assignment. So here I'm asking optimal cycle length as per Webster's method. So what is the optimum cycle length as per Webster's? Okay, so let's answer it. So as we know, it's for knowing the optimum cycle length, you need to know that L and Yi, summation of Yi's, and that we have already found in this previous slide, which is 0.716. So all we need to know is the total lost time. So the total lost time, which is capital L, here we have two phases, so it will be L1 plus L2, and then you will have the all red time. So in the problem data, you have lost time per phase as 4 seconds, and you also have all, this is all red time per phase, which is 1 second. So what you have is that for two phases, you have to add 4 plus 4. So that's lost time per phase, and all rate is 1 plus 1 because you have two phases. So this gives you 10 seconds. So once you know L, you can calculate C0, which is the optimum cycle length. This is optimum cycle length. So this is in the numerator, you have 1.5 L plus 5. This divided by 1 minus, you have two phases, so y1 and y2. So this gives you 1.5 times L is 10, then that's 5 divided by 1 minus 0.716, that is calculated from the previous slide. So this is 15 plus 5, that's 20 divided by 0.284. So that would be your answer in seconds. So let me calculate it. It comes out to be 70.42. Yeah. Did anyone got it right? Let's see. Yeah, 70.4 second. Yeah, correct. Yes. So let's move on to the next problem. So it's very simple, the other problems that are related here. So what is the total effective green time for the cycle? So here you have to calculate G total. So it's again very simple. G total is C minus L. C can be C0 here. So for simple, like simplicity, you can write it as C. So it's 70.42. L is 10 seconds. So it's simple, 60.42 seconds. Okay, so you can have some related questions here in the assignment. Let's see what else was given. Okay, so yeah, 17, that's correct. 60.1. Yeah, optimum cycle length, I think. Here you might have a different answer because the data is different here. And yeah, effective green. So yeah, we'll be asked this as, and you may be asked for some specific approach as well. So you know how to divide this G total to that approach depending on that yi values and the summation of it. So I think that's enough for this problem discussion. Let's move on to the next phase of this. So next is, I think, related to the second topic that I wanted to discuss was on okay. Okay, so next let's discuss this briefly. This is critical lane and time budget concepts. I'm not sure how much problem you will be getting in this part, but anyway, let's discuss. So this is critical lane, time budget concepts. So here, what you have is that critical lane is something which is used for identifying some spatial lane movements that will control the timing of a given signal phase. And time budget is something which is you are given some allocated time, budgeted time, maybe some 1 hour or so. And then you have to divide the entire signaling and so on within that time, like the total lost time per signal, the total lost time in an hour, and those kind of things, total effective green in an hour, and so it's everything that you'll be doing in 1 hour. Okay, is there any message? Okay. Where PHF term was used in this example, peak hour fact. Okay, this one. Yeah, so let me see. Is it required here? Okay, here I think we have to divide it by this. Let's see. Let me work it out. 340, that's eastbound. Okay, 420. Yeah, so I think let me get the saturation flows. So it's 1250 set. 36. Okay. Yeah, so what I understood, it's I think you have to adjust this hourly volumes in terms of PHF. So you have to divide it by 0.9 and then get this adjusted values, and then you have to, so those will be your QIJs, and accordingly I think you have to use this SJ and whatever you have. But anyway, in that other example it was not used, so I think you have to use it here in this problem, because that is I think some equivalent hourly volume that you have to calculate. So it's only the hourly volumes are shown here and you have to divide it by 0.90. Yeah, I think you'll be able to get it. It's just division of all these four numbers by 0.9. Okay, so let's move to the next discussion. It's on critical lean. So I think, discussing this time budget thing. So it's you have 1 hour, and within that you have to have those allocations like total lost time, total effective green, and so on. And the critical lane is something. So maybe I'll just write it down briefly. So critical lane is something the lane with most intense traffic demand. So this is not necessarily the lane with the highest volume. So this is the highest volume to saturation flow. So that is, and then you have maximum sum of critical lane volumes. You have formula for that, and then you have using total effective green time. You have an expression, and you can do some sort of a, like you can come up with some formulas for this appropriate cycle lengths and so on. So I think here also peak hour factor is relevant while discussing this. So here it's written that this is used to estimate flow rate in the first 15-minute period of the peak hour. So you typically whatever is given, you will divide it by this number. So I think there was one example that was also given there, and the flows are provided there, but you have to divide it by the 0.95 or 9, whatever number is given, to get this equivalent hourly volumes. So maybe I'll just go into that one example problem that was discussed in the class, and then I'll probably move to the next topic. So here Let's see if I can have that figure up. Okay, so so, so this example was, I think, given in the class where you have these two phases that are denoted here, and you have this one lane in this both directions, and the volumes are given as well. So the cycle length, total loss time, and saturation headway, peak hour factors, and everything were given. So you have to determine the cycle length, which will kind of satisfy the minimum required cycle length to accommodate the critical lane volumes. And if not, you have to find out the appropriate number of lanes that each lane group needs to have and the desirable cycle length. So that was the data that you had. And you first can come up with this critical lane flows, and after that you can add those volumes that are given, and if those cannot accommodate whatever the critical list should be higher than what you need to accommodate, so in that case you might be falling short as well. So in that case you have to check whether what could be the optimum cycle length. And if it turns out to be negative, so I think that was shown in the class, that then no cycle length can accommodate that flow at that locations. In that case, you have to go for multiple lanes. And by increasing the number of lanes in both these directions, you have to then check whether you can come up with a cycle length that will actually satisfy whatever this critical flow that you, lane flows that you need to accommodate at that location. So in that example, I think there were some recommendations that northbound movement should have 2 lanes and eastbound movement should have 3 lanes and so on. So yeah, I'm not going into that example again, but that was kind of the gist of that problem, and this is relevant in this context, that additional lanes can provide some in both directions, can provide some shorter cycle lengths and so on. So this has direct relations with the signal time designing that we'll be doing. So I think that was the main discussion of this first part of this module, Webster's method, as well as this critical lane groups and this time budget concepts and so on. So maybe I'll come back to it later if there are some questions in the assignment, but let's move to the next, I think, topic, which is the planning level analysis. So planning level analysis, to begin with, it's, I think, less computational compared to the operational level analysis. So let's write it. So here, like, the data inputs required for a full operational analysis are not needed here. Like, this is just some kind of a preliminary check. So estimating some signal phasing and timing, this some comparative analysis that can be done through this against operational performance produced by other methods and so on. So in this context, I think some methodology were discussed in Highway Capacity Manual 2016, and there are different parts to it. One was, I think, intersection sufficiency assessment. The other could be delay and level of service. So these are mainly some theory that were talked about uh, in general. And then I think there was some example that was given of some 2 4-lane arterial roads with demand volumes and some exclusive right turn and so on. And I think that example came later as well in solving some problems. So the main thing, I think, that's somewhat, I think, relevant to the assignment problem as well. So it's the steps that have been, I think, talked about. So the step one is the determining the right turn movements, the right turn operations. So the main thing here was that this permitted versus protected movement. So this is protected, this is, and there are three conditions that were talked about here. So one condition was this VRT, which is the right turn flow rate in vehicles per hour. This has to be greater than this. Condition 2 was VRT times V naught, which is the opposing through movement flow rate. Or VO, you can write. So this has to be greater than equals 50,000. So for one opposing lane and for two opposing lane and three opposing lanes, so on. So let me write for the first one only. And the other conditions are also there, so I didn't write it. And the third one is there is more than one right turn lane. So this, if any of the conditions, if any of the above conditions are met, then you have to assume protected operation. Okay, so we'll see, I think, one question related to this in the assignment. Next is the solution. So I think one problem data was given where this flows, different flows are given, and this based on this volume or the flow rate of the right turn. So you have to make those checks for every approach, say eastbound to westbound and this north or southbound. And if any of this condition is satisfied, then you have to go for additional checks for, say, if first you'll be checking the first condition. If it is not satisfied, then only you go for the additional checks. And then if both of them or one of them is satisfied, then you have to see like the protected movement has to be given in there. So those kind of decisions are relevant in planning level analysis. Then I think there is some talk on single phase plan. So whether an exclusive right turn phase A is to be used on, say, north-south arterial and so on. Then I think there are some additional examples were given where true and permitted left movements on, say, some north-south arterial can be allowed, or in an east-west arterial where whether there could be permitted right movements or left movements and so on. So the step two is the next one, which is the conversion of volumes to true volume equivalent, vehicle equivalent volumes. So step two here is conversion of volumes to true vehicle equivalent volumes. So here I think again different factors were discussed, and this discussion I think again appears in that operational analysis as well, like the effect of heavy vehicles and then pedestrians on left-turn vehicles, parking maneuvers, lane utilizations and so on. So you have a bunch of factors and you have to do some multiplicative, this factor should come up, and this equivalency factors you have to multiply it with some movement volume to get this equivalent true movement flow rate expressed in say passenger cars per hour, through passenger cars per hour, which is TPC per hour. Then you have to like there are different, I think, recommendations on this adjustment factors that are given in highway capacity manual, like what should be the adjustment for heavy vehicle, which is EHV, and this adjustments again can be different because of variation in flow during the hours and so on. So you have to do like a lot of factors you have to consider before making these adjustments. And I think there are some tables that were given for adjustment for right and left turning vehicles, then equivalency factor for lane utilization, parking activities, and so on. So I'm not going into the details of it. So it's just you can have a data with all this. You have to check in which criteria it fits in and just calculate those factors and just multiply and then just get this equivalent volumes or TPC per hour. So that's all you have to do. So it's very simple. So it's not, I'm going not into this detail. So next is the third step. So let's talk about that in the next slide. So the step 3 involves what are called defining lane groups and assigning flow rates to lane groups. So this is defining lane groups and assigning groups. So here again we have to assume the lane groups and the movement groups, those are not different. So this discussion I think was happened before in one of the weeks. So here in lane groups, I think you have to consider whether there are exclusive turning lanes or not. So left turn only or right turn only lanes, or like can be like the separate lane groups. And the remaining lanes can be combined, like through only lanes and some shared lanes and so on. So once you define this lane groups, you can come up with this lane group flow rate. Divided by the number of lanes associated with the lane groups to obtain lane flow rate. So something which is important here is the lane flow rate. So this is nothing but this whatever flow rate you have divided by number of lanes associated with that lane group. So that's very simple. So there was, I think, one example that was given in the class, which was having the movements of the lane groups defined for every approach. And you have the V adjusted, and the lane groups were also like defined. So let me see if I have the figure. I think it will be easier to understand. Okay. Let's see. So you have these three, say, different phases here. So in phase A, it's denoting this right turning. Then in phase B, you have this through and also this left turning, and this phase C, you have this as well, this in east-west direction as well. So here, for every approach, you have to see what kind of movements that are happening, whether it's left turning, whether it's through or right turning. So for example, in this eastbound, this one, what you can see is that you have a through plus left turn and you also have a right turn. So in westbound also you have a through plus left turn and you have a right turn. For southbound, for example, this one, So here you have true plus left turn, or you can have right turn as well. So from I think this one, and then you have the similar thing defined for northbound as well, true plus left and the right turn. And then you have to see how many lanes are there. And the lane group volumes, if that is given, then the signed flow rate, you just can divide the volume divided by the number of lanes you have. And that will give you the final answer, right? Then in this context, you might be having some problem related to the ring diagram. So that's step 4. So that's so step 4. So here you have what are called as determining the critical lane loops. So here also will be given, say, different phases, and the volumes will be given. Now you have to come up with what would be the critical flow of this lane loops or the approach, whatever you call it. So if there is one example, let's see. Yeah, I have think I'll be given a data like something like this for different phases, and from which you have to see which one you have to pick. So typically for this one, this phase A, you will be picking the maximum of this two, and that will be your in TPC per hour per lane. Here also, in general, you will be picking the like maximum of this two, and here in the final one as well, you have to like again pick the maximum of two. If you get all this, then it's just simple summation that you have to do to get the critical lane volume. So I think there is this problem in the assignment as well before that. Okay, let's see what was the problem that was given exactly in the assignment. So the assignment, let me open. Okay, so let's use this data and solve the assignment problem. Let me take this example. So here the data is again planning level analysis from highway capacity manual, and this figure is showing this ring diagram for a three-phase signalized intersection. As you can see, there are three phases A, B, and C, and all equivalent hourly volumes are given in vehicles per hour. So all volumes are given in vehicles per hour. And then you are given with some additional information. So one is target V by C ratio. Okay, so let's see. Okay, I think we have answered the first question. Is it something related to the assignment? Let me check. Okay, so in the assignment, the data is, I think, different. So that's good. But anyway, I think it comes to be, yeah, sorry, this one. Mhm. It's something different, but it's, it asks the same thing, critical lane volume, right? Okay, so you were given additional informations here. One is the target V/C ratio, which is 0.92, lost time per phase, which is 3 seconds, and then you have summation of this Y values. I think that would be useful in a later problem where you have to determine the estimated cycle length. So, but I think it goes on to the other problems as well, the delays and so on. But anyway, let's first answer this. So you have this YC1. How many phases you have? Okay, 3 phases. I think YC2 plus YC3. This is equals 0.752. So I'll explain what this is later. Base saturation flow is also given for all approaches. So this is 1.9. Okay. Yeah, so the additional data I think is required for other problems. So maybe I'll come back to that later. But the first problem that I've given is to determine the critical lane volume. So the answer is simple here. The first one is 258, the next one is 720, and the third one is 450. So if you add that up, you will get uh, 1428 vehicles per hour. Is it the answer that got? Yeah, that's the correct answer. Yeah, so the next problem I think is something related to this estimating the cycle length as per the target V/C ratio. So for that you have a formula, but I think that comes sometime later. But anyway, let's quickly discuss that. The next problem is estimate the cycle length as per the target V/C ratio. So what would be the answer to this? So the formula is C equals L times XT divided by this XT minus this YC1 minus YC2 minus YC3. So here This L is the total lost time that you have to calculate, and xt is the target V by C ratio that we are looking at. So you have three phases, and then the data, I think lost time per phase is given as 3 seconds. So your total lost time is 9 seconds. Then you have this 0.92, which is your target, divided by you have this xt, which is 0.92 minus 0.752. So that would be your answer in seconds. So did anyone get anything? Assignment 7, Q17, 1402. Okay, I'll check. I'll come back to it later. So this one you're saying it's 49 seconds. Yeah, I think that's correct. That's good. 0.68. It's 49.29 seconds. Yeah, that's correct. Then you may be asked about the effective green time for phase B or phase A, whatever it is. So what you have to do is first you have to get G total, which is C minus L. You know C and L is also known. And from that you have to do a distribution, which is that VCI divided by VC. So the critical lane volume is VC that you got, and VCI is you have to find out through this diagram. So let's maybe solve it in the next slide. So the problem data remains the same, and now we have another questions that asks you what is the effective green time for phase B, suppose. So the way to do it is that first you have to calculate this G total, which is C minus L. C is your cycle length that you have, I think, calculated, which is 49.29. And your L is 3 times 3, which is 9 seconds, that you also have used in the previous calculation. Once you have it, for this phase B, you can write this is G total times this V of CB. So instead of I am using B, divided by VC. So this gives you 40.3. For phase B, it's the maximum between 556 and 720 as the volume. So we'll put 720. And VC is the critical lane volume. You have calculated 1428. So this gives you the answer. I think it will be around 20. Is it? Let's see. 20.32. Okay. So that would be your effective green time for phase B. So that was again a simple problem. Then you may be asked about some more problems, but then incremental delays and so on. I think I'll get into it later if I have time, but maybe just get into that other discussion. But first, I think someone said about this Q17 of assignment 7. You're saying 1402. Let me just quickly check. Okay, 1402 is one of the options anyway. Yeah, probably you are correct. It's 250 plus 556. Let me calculate and confirm. Yeah, so yeah, I think you're correct. That would be the right answer to this. It's simple anyway. Same logic applies, but you have to just check that this entirely, like this plus this and this plus this, and you have to take the maximum between those two, and then you have to, you know this. It's very simple. So it's a two-phase thing here, or you can think of it as four phases as well. Okay, so let's get into the other discussion. So I was discussing the planning level analysis. So let's quickly see what's left there. Otherwise, I'll just briefly discuss the operational analysis. Yeah, so in this, I think I was in step 4 that I'm discussing this determining the critical lane groups and the volumes and so on. I think the fifth one is assessing intersections efficiency of this estimated or this estimating cycle length. So yeah, in this context is the one I think that I just discussed. So you have maybe having a target V by C ratio, and then you can come up with some calculations. Okay, so let's not get into the details of it. Then you may be asked about this yeah, minimum cycle length for this target V by C ratio that I have already talked about. Then the other problems are like cycle length calculations, and okay, step 6 is calculating green times and VYC ratios. Green time calculation I have shown in one of the examples as well. And yeah, there can be bunch of calculations that that you have to do. For every phase, you can find out this effective green times and so on. Then I think there are these calculations on capacity and VYC ratios, determining delay and this level of service. I think this discussion again appears in the operational analysis. So based on this PYC ratios as well as control delay, you have to check what is your LOS. Yeah, and if VYC is greater than 1, then you know for sure that it should be F. Okay, so I think that was all about the planning level analysis. Next is the operational analysis. Let's get into that discussion briefly before I'll move on to maybe solving some of the remaining assignment problems. Okay, so it's operational analysis. So here, it's again you have this bunch of steps. So the ones that are important here is step 3. It's determining the lane group flow rate, determining then adjusted saturation flow rate, and these are dependent on each other. So it's kind of one, it's an iterative process. You update one and you have to update the other one again and so on. And I think finally, after determining LOS, the step 9 is something which is also new. It's determining Q storage ratio. So let's maybe discuss very briefly these things, or maybe just jump into the assignment now and then solve it. Okay, so let me see if there are any relevant problems to it. Okay, I think there are a couple of questions that are relevant to this operational analysis. Oh, let's see. Okay, I think there is one. Let's talk about this one. So it says that again it's matching the types of lane loop operation with omitted terms in estimation of adjusted saturation flow. So it's related to adjusted saturation flow and relation of lane loop operation with omitted terms. So omitted terms in estimating this adjusted flow. So we have this columns. So let me the first one. So it's column X and then I have column Y. Permitted NT operation in shared lane. It is one is protected LT operation in shared lane. Then three protected RT operation in exclusive lanes. And four is protected operation in exclusive. Okay, and here you have FLT FRT FLBB, for B you have FLT LBB, BB, C is F L U B F R T R and D is F L U F R T and F R P. So what would be the answer to this uh, question? So let's see in this context what was there in the material. So in operational analysis, it was discussed this all this adjustment factors to get the adjusted saturation flow rates, but all of them are not required depending on the conditions that you have, and you have to check for which are the terms that are omitted. So LU is something which is related to lane utilization. LT is related to left turn vehicles. RT is related to the right turn vehicles. LPB is left turn and the pedestrian and bicycle adjustments, and RPB is for right turn. You have this pedestrian and bicycle adjustments. So when you have, I think, of protected, sorry, the first one is, I think, permitted left turn operation in a shared lane. So in that case, I think the ones that are omitted are this LU, RT, and RPB. So one would be D, I think. Let's see if anyone answered this. Okay, 1D, 2A, 3C, 4B. Okay, let's see if that's correct or not. So I think A is correct. So that's, sorry, it's 1D. Let's see what 2 is. So 2 is protected left turn operation in a shared lane. So in that case, this LU, LPB, then RT and RPB, that's the one you have to omit. So I think it comes out to be C, I think. So, but some you said A, is it? Okay, 2 is one. I'm not sure. Like it should be, I think, U T. 2 is, I think, should be C. Next, okay. Let's see. 3 would be 3 is protected right turn operation in exclusive lane. So for protected right turn or through or whatever in exclusive lanes, the things that are, I think, omitted are FLT, FRT. So the first one is for, I think, left turn, is it? So then should be FRT. Let's see. Okay. Um, RT, LPB, and RPB. RPB. Okay. think there is some issue with the options. 3 should be, I think, it is 4, protected through operation and exclusive lane. So ADRT, PB, 4 should be A. That leaves with us with 3 with B. Uh, Protected RT operation in an exclusive lane. So that's LT, LPB, and RPB. Okay. Now I misread it, so that's fine. 3 should be P. This would be your answer to this problem. I think someone mentioned it. DACB, is it? Okay. Okay, so yeah, I think because probably you answered a different question. The order is kind of different here, maybe that's why. Okay, so let's get into the next problem. Let's see what's relevant in here. I see more questions on planning level analysis mostly. Then, okay, let's solve this problem. It's maybe relevant. Okay, so here we have the capacity of lane group for signalized intersection is 625 C per hour. Next is you have duration of each analysis period. The duration of each analysis period is 15 minutes. The demand flow rate for the lane group are given during each 15-minute period. The demand flow rate of the lane group during each 15-minute interval is, so let's create a table. So this is analysis period. Then you have demand. So this is from 0 to 15 minutes. Then you have 15 to 30 minutes, 30 to 45 minutes, and then you have 45 to 60 minutes. So here the data is given, say 6:45, 6:37, 6:49, 6:57. So you have to estimate the length of the queue at the end of 60 minutes. So this length of the queue is in terms of C, and you have to assume there is no initial queue at the beginning of the first 15-minute interval. There is no initial queue the beginning the first 15-minute. So this is the data and you have to solve this problem. So let me solve it in the next page. Maybe you can take a picture of the data. Then I'll move to the next page. So here you have 4 analysis periods, each spanning 15 minutes, and the demand is given. The capacity is also given for that signalized intersection. And if V and C, like the demand and the capacities are given, you can calculate the values of this other terms, which is directly related to the length of the cube. So here, I think should be let's see how we can solve this. So So if V is greater than C, then you have a formula for it. So T is the duration. Okay, I'll write it down, but let's see if anyone sent anything. Yeah, P greater than equals to C, that's correct. T is equals T. Okay, so I'll move to the next slide. So the solution. So what you have is this equation, which is QE, I think, equals QB plus T times V minus C. So V and C's are given. So your QB is the initial Q at the start of the analysis period. So that's 0. QE is the Q at the end of the analysis period. So that you have to check. Then you have this capital T is the analysis period duration. That's in hours. And small t is the duration of unmet demand in the analysis period. And that's all the data we have. So let's, I think, get into the calculations. Okay, so for the first analysis period, let me maybe make a table and that would be clearer. So it's, so here I'll write it down as analysis period. Then you have this small t in hours. Then you have this V in TPC per hour. Next you have this C, actually this small v. So then you have QB, and you have QE. So the first analysis period, this is of length 0.25 hours because you have 15 minutes. Demand is 645, capacity is 625. So this is 645, this is 625. Initial QB is 0. Then you have to just put this to get QE. So this is 0. Then you have T, which is 0.25. Your V is higher than the capacity. So that's 20 this part. So it's 20 times 0.25 and this becomes 5. Now this 5 will become the QB for the next part because this is kind of related to the unmet demand, which is the QB term. Here for the analysis period 2, you have 0.25. V is 637. So this is 637. This is again 625. QB is 5 now. So this difference is 12. This is 0.25. So that will be, I think, 3. So this 3 plus 5 is 8. 8 will come here again. Next is this 3, 0.25. This is 625. Let's see what was this. This is 649. And if you do the calculation, it's 8 plus, so this difference is 24 times 0.25, which is 6. So I think it's 14. Then again 14 will come here. So this is at the end of the fourth analysis period. I think this was 657, is it? Yeah, 657. So now this difference is 32. So that's 25 times 32. Okay, so that will be 8. So that's 14 plus 8. That's 22. So 22 is the final answer. So your length of the queue at the end of 60 minutes is this 22. Let's see if anyone got it. Explain problem once again. Okay. Yeah, answer is 22. Yeah, that's correct. So you have a signalized intersection with this capacity 625, this TPC per hour, and this each analysis period is having this duration of 15 minutes or 0.25 hours, and the demand flow rates for the lane group during each of these intervals are given. Now, if you notice, all for all these intervals, the demand is more than the capacity. So it's always there is some queue that will be building up at every analysis period. And as you have already mentioned, that this formula is applicable in that case. QB for the first analysis period it is 0 because the initial queue that is also I think written. Assume there is no initial queue at the beginning of the first 15-minute interval. So now at every interval, so this is the difference v minus c. This you multiply with time t and whatever is left over from the previous analysis period, you add it up and that will give you the total length of the queue. For the first one, there are 20 TPC per hour kind of extra spillover that is happening. And if you multiply it with time, you get it in terms of this length of the queue in TPC. And you didn't have anything from before, so that's 0. And then you just have to do this for every analysis period. So after the first analysis period, you have this 5 as the length of the queue. So that will remain as it is. And then there is this extra term that is coming for the second analysis period and so on. So that's the whole problem. So let's see if there is something related to this in the assignment. Okay, so the numbers here are different, but the approach would be exactly the same here as well. So I think that's good enough for this problem discussion. Okay, for this one is it 24, is it? Okay, so yeah, you have to work it out. I'm not doing it right now, but yeah, that could be the answer. Yeah. Last is 10 plus 14. Okay. Okay, till this point maybe it was 10. Okay, you're saying it's 14. Yeah, it's 40 times 0.25. Okay, that's 10. 10 comes from here. I think till this point you had some 14. So, okay. Maybe that's the case. Yeah, that should be the correct answer. Okay, so let's see if I can solve some more questions. Okay, so let's see what I had covered. This one was done. Okay, so in this context, I think I can solve another problem or like more of a true false kind of a thing. So let's see. So right, false. With respect to the Q at the end of analysis period, considering initial Q, which is QB, and V by C ratio at an approach of signalized intersection. So let's see. The first statement This is if QB is greater than, oh sorry, it is equals to 0. That means there is no initial Q, and to B greater than C, there will be no Q at the end of the analysis period. That's the first one. Next is if QB equals 0 and B greater than C, there will be a Q at the end of the analysis period. So this is the discussion we had just now. It's the same question in a different way, right? So I think you'll be able to answer it easily. So if now QB is greater than 0, that means you have some initial Q, and this V by C is this. The Q at the end of analysis period will be greater than, greater in size than initial Q. And the fourth one is if QB is greater than 0 and B less than C, the Q at the end of analysis period will be greater in size than the initial Q. It's the same state. So what would be the answer to this? I think it's very simple. We just now had this discussion. Okay, anyone has a doubt to this? Or did anyone reply? Answer is A and C. Okay. Yeah, that's true. That's the same thing. Answer is A and C, or you meant B and C? First one is false, right? Because the V is greater than C, like at the end of the analysis period, then there will be a Q. Yeah, this is also true. Last one is false. Why A and C, right? It's first one is false. Second one, which is true. This is just now we had this example. This part is 0. V is greater than C. Now we have this as something which is greater than 0, right? Anyway, I think you'll be able to get it once you go back and check later. But let's see. Or is it a different question someone was talking about? Assignment number 7, Q3. Question number 3. Is it estimated? Okay. Assignment 7. Okay, this one. Okay, I have to work it out with this data. Like, I don't think it cannot, like, it should be estimated. You will be able to, I think, estimate it. But which value you will be getting, you have to check. That's what I think, yeah. So it's the other one is 1 minus, yeah, I think. Here also, I think there you'll find some cycle length. It's not like no cycle length can accommodate the critical volume. Yeah, I think you should be able to work it out. So it's finding this effective green for this one, right? option B is correct or not. Check this, I'm not sure. Okay, so Webster's method, I think you have to. Phase E. Okay, I see. So yeah, generally you find out the phase-wise effective green, and for the westbound one, okay. But I think just a minute, it's QIJ. So you have the YI values, the summation of the YI values. Okay. Yeah, this seems to be confusing. I think you can estimate it. Should be false. But again, there is no clarity as such because you can get your QIJ by SJ for westbound, uh, this one. So saturation flow is known. The skew values are also known. So that kinds of acts like the yi for that portion, and then you have the summation of yi, and then you multiply it with the total effective green time. Then you should be able to come up with a number, I think. Yeah. But effective green generally happens for a phase and not just the. Yeah, even I'm confused about it. There is no clarity to this. I don't know. Maybe, yeah, maybe you can take that route and estimate something and check whether the answer falls within that A, C, and D ones and not B. I think it should be false, but anyway, let's see. Okay, you are getting answer. Y is, oh, okay, Y is 1.454, is it? No, I think Y should be around 0.71 or 0.79 something. I'm not sure. It shouldn't go above 1. So we will be getting something like 1 minus summation of Y should be less than, or rather, I think greater than 0, right? So this will be not sure. Yeah, sure. Yeah, I'll show it. Yeah, this one I'm confused. But this one, I think we just had a calculation. So this summation of yi, I'm not sure for this problem. Is it 1.454? I think I got below 1 anyway. If you are getting it as below 1, then you'll be able to estimate this as well. And once you're able to estimate this, I think you'll be getting some values here. Yeah. So yeah, this one I think, yeah. Is there any doubt to this? Because I think this was clear through the previous example as well. Okay. So yeah, the third problem is somewhat doubtful to me. I'm not sure. But for the first one at least, I don't think you'll be getting it above one. So let's see, since there is only 10 minutes left, I'll just maybe quickly go through the assignment once and check if there's something that I missed out. So yeah, this one is something which is doubtful. Yeah, this is only from planning level analysis. I think all the factors and everything are given, so it's just working it out shouldn't be too difficult. This condition 1, 2, 3, I think I've already talked about. So this is, I think, directly from the slide. This you have to calculate, and this one as well. So this LOS analysis and so on. This is again, I think, very simple, true and false. I think you can answer it. This similar problem I have discussed. This have been discussed. Okay. So the following. Okay. So I think this is again directly from the slides itself related to the gain groups and the movement groups. Next is, I think, yeah, this is also direct from the slides. Okay, yeah, this is also, I think, discussed. It's, yeah, these are also discussed towards the end of, I think, operational analysis. This I have discussed. Uh, this problem, okay. Yeah, this was, I think, similar to a discussion that we had. Yeah, I think it's there in the slides also. This discussion, I think we have. Okay, let's see, maybe if I just wrap up with some one of the questions and maybe just wrap it up. Let's see which one I can solve. Which one? Okay, maybe just wrap it up with some true false type questions, which is not directly, I think, there in the assignment. So state true or false. This is in the context of incremental delay. Incremental delay factor counts for the effect of controller type on delay, screen metering, adjustment factor is 1 for all coordinated intersections. And you have the variance in number of arrivals per cycle decreases with increasing by C ratio. Okay, is it related to? I think I'm going into the discussion of the actuated controllers. I think this is a discussion for next week. But anyway, let's answer this three. See if it was there in the slides. This, yeah. So I think yeah, this was discussed in the class. Yeah, incremental delay factor accounts for the effect of controller time on delay. So that's true because it's 0.5 for all pre-timed controllers and different values for actuated controllers. Then upstream metering adjustment factor is 1 for all coordinated intersections. So this is the okay. The variance decreases with increasing V by C ratio. This is also true. Okay, and the other one is I think upstream metering adjustment factor is 1 for all coordinated intersections. I think this should be for all individual intersections. So this should be false. Yeah, so I didn't go into the discussion of this later portions, but I think there were very few questions related to this from in the assignment. And this one was, I don't think it was there in the assignment as well. Okay, so it's almost time. So is there any doubts? Okay, if k equals zero point 0.5, yeah. Was there, this question was there in the assignment? Um, yeah, I think it should be false. Yeah. In the slides, I think it was written about some individual intersections. Yeah. Okay. So, yeah, I think I'll wrap up for this week. Next week, I'll be discussing the content of week 8. Yeah, I think I'll be able to answer the assignment problems. There are, I think, one or two doubts, like the third question is having, we are having a doubt and so on. But yeah, that's all. I think if you have any more doubts, you can always post in the discussion forum. Hopefully, someone will answer it, the TA of the course. And yeah, the other issue should be resolved in terms of wrong answers if there are any. Okay, so if you don't have any doubts or such, then we can close the session. Okay, Q5 and 6. 5, 6. Okay, yeah, so this is somewhat involved, right? So I think, yeah, just follow the slides. I think you'll be able to answer this. This is from planning level analysis. So you already have this factors and everything given. Yeah, this one, two, okay. Opposing volume traffic, number of opposing lanes, okay. So everything is given. So what is the value for equivalent flow movement? So we adjusted for right turn movement. So I think it's direct formula. It's not that difficult, right? Let me just quickly check. Yeah. So it's V times all these factors multiplied. V is given and 526 vehicles per hour, and all these factors are also given. So just multiply all those and you will get the answer. And then for a lane group of signalized intersection, the demand flow rate and capacity are given. Control delay for the given lane group is given. The level of service you have to estimate, right? So V by C ratio you have to find out. Control delay is given. So with that, there is a table. From that, you can answer it, right? It's not that difficult. This is also easy. Okay, 890, 900. Yeah, you have to work it out exactly what would be the multiplication factors. I'm not sure, but you have to check. And this one is, I think, very simple. Without even calculation, I think you can answer this. It should not be a difficult one. Okay, so I think this is a simpler numerical compared to others. Okay, the data is also given. Yeah, here the demand volumes are given. Okay. Oh, this is opposing volume traffic. Okay, from here you have to get the V value. Yeah. Okay. Yeah. Maybe that would be the correct answer. But yeah, do work it out and see if that's correct. Okay, I think the other numericals are kind of discussed. Maybe this one is, yeah, this is also directly from the slides. It should not be a difficult one. Okay, so no other questions. We can close the session. Feel free to leave if you don't have any more doubts. As per planning level analysis of an intersection, absence of protected phase for right turning vehicles is justified if there is more than one right turning lane on that approach. I think this should be false. Let me just check and confirm. Yeah, This is false. Yeah. Yeah, I think this was also there in the slides. It's direct message. Yeah, I think this was again related to that three conditions. I think that was the condition one, two, and three. Third condition was related to those one. Q15 is it? Okay, like what's so difficult here? I think it's you can work it out, right? It's just a ring diagram and all the data are given. So yes, see, okay. Numerical values indicate the V/S ratios. Okay. Okay, these are the V/S ratios. It's not the volumes. Some of the critical include V/S ratios. It's- It should be easy, right? It's 3.47. So yeah, it should be from one of these options only. So I just worked it out. It like I'm not giving you the direct answer because that's the goal, right? You have to solve it on your own. Like look at every individual phase and how would you work it out and so on. So these are not volumes here, it's V by S directly. So accordingly do the calculations will come up with the answer. Option B is correct. Yeah, probably that's correct. Yeah. You have also worked it out, I think. Yeah, that should be the correct answer. It's greater than one, this condition is possible. Critically by C. Yeah, maybe possible, but I'm not sure. I have to work it out with these values that are given. Let's see. This was about some again. Critical by C issue. So C is what is the 60 seconds. That's the cycle length. Total lost time per cycle is 9 seconds. So that's 60 divided by 51 and the sum is like okay. 6. Yeah, I think in this example you might be getting it more than one. That's what I feel. Yeah, I worked it out. Yeah, that can be a correct answer, but I'm not giving you the answer as such. Yeah, that can be a possibility. So it depends on that C by C minus L thing. So C by C minus L can be very large, even like greater than one. That multiplication might end up being greater than one as well. Okay, anything else or I'll close it. 17A set. Yeah, I think we previously told that 1402 is the correct answer. So I think that should be the case. Yeah, so see you next week then.